You don't want to miss this. This is so cool. It shows why abstract algebra is so beautiful. So in intro group theory, we learned that inverse elements in a group are unique. So for example, the fourth axiom of a group says that every element G in G has an inverse element, which we call H, such that GH is the identity, and that's also equal to HG. So this is actually encapsulating two properties, that H is a right inverse of G and H is a left inverse of G. GH is E is H is a right inverse, and HG is E is H is a left inverse. Then we know that the inverse element in a group has to be unique. Now here's something so beautiful, which is the theorem I'm going to do in this video, that suppose you have a monoid, so it has a binary operation, it's associative, and you have an identity. Okay, and suppose every element in the monoid has a one-sided inverse. We don't know that it's a both-sided inverse, but we know at least every element has either a left inverse or a right inverse. Then we can prove that actually the monoid has to be a group, that every element has a both-sided inverse, and then the inverse is unique. How cool is this? It's such a beautiful theorem, and it's going to be so great. I'm just going to show it to you right now. So let's just dive right into it. So what we're going to prove, so here's our proof. We know that every element has a one-sided inverse. We have to show that that inverse is also the other-sided inverse. It's a both-sided inverse. So let's start off with an element x, okay? So let x be in G, and let's assume, we know that x has a one-sided inverse. Let's assume, without loss of generality, that x has a right inverse, okay? So the x in G, and let y in G be a right inverse, okay? So we have a right inverse of x. What does that mean? That means that x times y is equal to the identity. Now what we want to prove is that yx is the identity, and that will show that y was actually an inverse of x, and therefore, M is a group. The monoid we started out with is a group because every element has a both-sided inverse. Now this isn't obvious. It's quite possible in a monoid, for single elements to have infinitely many left inverses or infinitely many right inverses, okay? So what we're doing here is we have a monoid where every element has a one-sided inverse, but you can have monoids where some elements have one-sided inverses and have infinitely many of them, other elements don't. Okay, so I will direct you to the video which shows that at the end. But let's actually now prove that yx is the identity. And so if you're enjoying my content, please don't forget to leave a like and subscribe. It makes a huge difference, and I love every comment I receive. So drop a comment down below on what your thoughts are. But here we have xy is the identity. We want to prove yx is the identity. So what we're going to do is we're going to call yx z. Okay, z is yx. We want to prove that z is the identity, and it's so cool. So we're going to actually consider z squared. Okay, so z squared is going to equal to yx times yx. That's what z squared is. And associativity tells us that it doesn't matter how we multiply. We can multiply yx and then yx, or we can redistribute the parentheses. We can multiply y, then multiply xy together, then multiply x. We could do it that way too, and that's perfectly fine. But we know that y is a right inverse of x, so we know that xy is the identity. So this is going to be y times e times x. And y times e times x, well, e is the identity. So again, it doesn't matter how we multiply. You can multiply y and e, or you could multiply e and x and then multiply the other one. So here we have is just going to equal to yx, which is of course z. So z squared is z. And here's what's so cool. Z has to have a one-sided inverse. We don't know what side it is. It could be a right inverse or a left inverse, but z has a one-sided inverse. So knowing that z squared is z, now what we can deduce is that let w be a one-sided inverse of z. Okay, it doesn't matter. Let's assume w is a left inverse. Okay, it doesn't really matter. Either way the argument's going to work. So let w be a left inverse of z. And now what that tells us is that, of course, wz is equal to the identity. And now we can actually complete the proof. So I'm going to do it up there. W is a left inverse of z. So let's get into it. So now we know that z squared is z. So therefore, wz squared is equal to wz. And because w is a left inverse of z, that means wz is the identity. So this is going to be wz times z is equal to the identity. So therefore, e times z is equal to the identity. Therefore, z is equal to the identity. But therefore, yx is the identity because that was what z was. And now we conclude that y is a left inverse of x, knowing that y was a right inverse of x. So every element in M has an inverse, and this is a really beautiful proof. And it's very subtle, as I said. You know, you can have a monoid where some elements have infinitely many one-sided inverses, and the only way that can happen is there have to be some elements which don't have any one-sided inverse, because of what we just proved. And if you want to see that video, it's going to pop up on the screen here. It's a super fun, beautiful example of such a monoid. You're going to love it. And if you want to see a mathematical structure with infinitely many identity elements, okay, so it's a semi-group, it has a binary operation, it has associativity law, but there are infinitely many identities. How does that work? And a proof that identities are unique. So the second half of the video will show that there are a structure with infinitely many identities, but you can check out that video here.